identify them as cis and trans isomers. So remember, again, these are really sort of what happens when we have those double bonds. They kind of lock everybody into place. And when you're first trying to identify, again, cis or trans, really the best thing you kind of do really is just kind of draw a box around the double bond. And again, you want to double check that on each of the carbons, we do have different groups like we do here and we do here. Then obviously we need the same group on opposite carbons. So we do have a methyl group here and a methyl group here. Or you could even look at the bromine group on opposite sides. These are both opposite, which means that obviously this would be trans. And now we do want to locate or really name it properly. And as I mentioned there at the sort of very end, it is very, very common that people sort of in this situation, especially when it's drawn in the sort of cis or trans sort of way, so they just kind of focus in on the two carbons in the middle. Again, we were still looking for the longest carbon chain. So again, starting up here would be 1, 2, 3, and 4 carbons, which much like the one above there will also be butene. Now, we want to number the double bond. In this case, we could go 1, 2, 3, 4, or 1, 2, 3, 4. In either case, our double bond ends up at carbon number 2, so there's no difference no matter which way you go. Also, in either case, our groups here end up at 2 and 3. Our 2 and 3 also does not make a difference. So actually here, that is 1 bromol group and 2, and that gives us trans 2, 3 dibromol. So I ran out of room. 2-butene would be our name here. Any questions on that name there? Now, if we look at the last one here, we're going to focus in here on our double bond. We see 2 different groups there, which is good. Other carbon, also 2 different groups, which is good. The same group on opposite carbons is again our methyl group. We see it opposite sides. You could also look at the hydrogen if you wanted to. So this again is going to be a trans situation. And in this case, get rid of some of the mess here so we can kind of see. Going with our carbons, longest continuous carbon chain like we did above, still the 1, the 2, the 3, and the 4 in this case. Really nothing else attached. So in the case of naming, hydrogen not really named or anything like that. So this is just really 4 straight carbons, and the double bond at carbon number 2, no matter which way you go. And that would then give us trans 2-butene. Any questions on cis or trans? And again, as I mentioned before, you know, if you had something like this, if we were to isolate here our double bond, different group, this group and this group is the same. So again, no cis or trans possible. So those are 2 important things to be able to have that. You got to have those different groups on each of the carbons, and then you got to have a group that's the same on both. Any questions on cis or trans there? Then let's actually talk about some of the reactions that these alkenes undergo. So unlike alkanes that we talked about, that they undergo substitution reactions, alkenes actually undergo what types of reactions which are referred to as addition reactions. And unlike substitution, where something comes off and something goes on in its place, in an addition reaction, we actually just put 2 things on. So nothing necessarily comes off. We just kind of put two things on. So here we go. Here's basically the general deal on this type of reaction is you have an alkene. It's got a double bond. And you basically add something to it. Could be two of the same thing, like Br2. Could be two different things, like HBr. But what always happens in this case, absolutely positively in these type of reactions, is you should only be concerned with right here. This is the only part of the molecule you should be concerned with. If there happens to be 400 other carbons attached there, doesn't matter. Everything's going to happen right here at the carbon-carbon double bond. And basically what happens is the same thing always. This carbon-carbon double bond becomes a single bond. So in this type of reaction, the double bond here becomes a single bond. So all you have to do is copy it exactly the way it is written over there. Turn my double bond into a single bond. And the purpose for that is when we look at the alkene, the carbon over here and the carbon over here, it's full. It's got 4 bonds. So to make room for these guys that are coming in, we got to get rid of a double bond. Now we have room. And one of these guys goes to this carbon. The other guy goes to the other carbon. And basically, we just put them on. Oops, if I could write it correctly there. There we go. H. And we end up with something that looks like this. We go basically from an alkene to an alkane. Double bond to single bond. So that is 100% of the time you have an addition reaction. That's pretty much all you have to remember. Double bond to single bond. Put one of the guys coming in on one carbon, the other guy on the other carbon. Any questions on that there? Now, there are certain types of addition reactions. There are certain types that are sometimes referred to as a symmetrical addition. And what a symmetrical addition basically means is you're adding 2 of the same. So for example, H2, which basically means you're adding 2 H's. Br2 means you're adding 2 Brs. Cl2 means you're adding 2 Cls. These are symmetrical additions, which means essentially you can't mess it up because each carbon gets the same element. So those are pretty easy. There's also some unsymmetrical additions, like when we add something like this, which is basically water. H2O is added as H and OH. These are unsymmetrical additions. Which basically means we're adding 2 different elements. Like water, H2O, like HBr, like HCl. Now, in all these cases, there are a couple of names. One is a hydration, one is a hydrogenation, and one is a hydration. Hydration will sometimes require catalysts, and that's what these are. You'll sometimes see these on top of the arrow, which basically doesn't really do much other than speed up the reaction. So again, if we had something like this, and we added H2 to it, although there's a lot of carbons going on there, we would just want to focus in on this. So as I mentioned earlier, the nice thing about doing sort of the reactions and drawing the reactions is you pretty much have the answer there. So I absolutely just need to copy exactly the way it looks. The only difference is, as we talked about, we're going to make the double bond into a single bond. So nothing crazy happens, nothing becomes a ring or anything like that. We're just going to simply copy exactly what's there. And when we get to our double bond, we're going to make it a single bond. And actually, I probably should draw it lower so we can actually see it here. Kind of cut off. We go over in this spot, I think. So again, I'm just going to copy it exactly the way it looks. I'm not going to change anything other than that double bond to a single bond. And now I have space on both of my carbons for each of these hydrogens. So we put this hydrogen here. And we put this hydrogen here, for example. And that is all they wrote there. Everything is exactly the same. Double bond became a single bond, one hydrogen to one carbon, one hydrogen to the other carbon. Again, we went from an alkene to an alkane in this case. Any questions on that there? So this type of reaction where we add hydrogen is sometimes referred to as a hydrogenation reaction. It's a fancy word for like we're going to add some hydrogen in there. And that's what is referred to as a hydrogenation reaction. There is nothing different other than break the double bond and put a hydrogen on each case. This is definitely considered a symmetrical addition because you're basically adding the same element to each side. You can't really screw it up in a sense. This is kind of what they do when you hear of things being partially hydrogenated, you know, like margarine and stuff like that, partially hydrogenated oils. They basically are breaking some double bonds by putting in some hydrogens to make it more saturated from unsaturated. Unsaturated right in our alkenes where we have double bonds to more saturated where we have more of the maximum number of hydrogens. So again, you could do this even with anything that is symmetrical and the same thing is being added. So why don't you try one here? Again, works the same way as hydrogen, but we'll use like Br2. So let's just say we had, let's say we had this. And let's say we added some bromine to it, Br2, which is basically Br. All right, why don't you draw the product here of what you would get? Again, follow basically the same example I just showed you with the hydrogen and see what you come up with. So again, even though this may look bigger, we do see the double bond, so we know it's going to be an addition reaction. We see this is again a symmetrical addition because we're adding two of the same elements, in this case, two Brs instead of two hydrogens. Works the same way. We should only be concerned with really one part of this molecule, even though there's a lot of stuff in there. And that one part is simply right here where our double bond is. And what we know is by understanding this reaction, that pretty much everything remains exactly the same, except our double bond becomes a single bond. So really, I have my final structure really right there. I could just copy it exactly the way it is. Again, I'm not going to do anything crazy or anything like that. The only thing I'm going to do at this point is take out a hydrogen that I shouldn't have had there to begin with. But other than that, that would be good. That's too many bonds to carbon. There we go. So there you go. Sorry about that. So I would draw it right the first off. But again, here we will make that a single bond at this point. Everything else is going to remain exactly the same. And now that I got rid of that extra hydrogen, I'm sorry about that, should not have been there to begin with. Now I actually have room here on each of those carbons for really both of these bromines. Again, one will go to one carbon, one will go to the other carbon. So again, we'll just do a Br there and a Br there. And again, this one to here, for example, and this one to here. Any questions on symmetrical addition reactions? Okay, so why don't you try this one? What is write the equation for the hydrogenation of 1-butene using a platinum catalyst. So why don't you draw all those structures, both of those things you should know. So hydrogenation is adding hydrogen. So let's see what you come up with. All right, let's take a look. So we want to write the equation for the hydrogenation, which again is a fancy word for I'm adding H2 or two H's. Of 1-butene. So that is what we're starting with. So butene, ENE means double bond. Butene or butane means 4 carbons. So that's actually what we're starting with over here is 4 carbons. 1 is where the double bond is located. I'll call that bond number 1, and I'll just draw out all the other hydrogens here. Try not to put too many extras on there. So we'll do that, and this, and this, and this. So that is 1-butene. We're going to add hydrogen to it using a platinum catalyst, which again typically would go on top of the arrow there. Not really doing much for anything in terms of product or anything like that. Again, what we have set up here is our addition reaction of our alkene. This again is a symmetrical addition because we're adding 2 of the same elements. And as we've been talking about, all we want to do is focus in right about there. And the only thing that's going to change here is we're going to make that double bond into a single bond. So literally, I'm just going to copy this thing kind of exactly the way it is, except making that double bond into a single bond. So that's what I'm going to do right there. Everything else exactly the same. Don't try to make anything different. Just copy pretty much what you got going on there. By doing that, we have now essentially made a spot at this carbon and a spot at this carbon for each of these hydrogens basically to be attached. So I'll draw them a different color here. One hydrogen will end up over here. The other hydrogen would end up over here. Again, we went from an alkene on the left to an alkane on the right. We went from 1-butene to butane on the right. Any questions on that reaction there? All right, so let's go this way. So as I mentioned before, this is a very common process of the hydrogenation of oils. Is sort of how you make things like margarine and stuff like that. A lot of oils and vegetable oils have double bonds, so adding some hydrogen to it makes them a little bit harder. So oil obviously is more of a liquid. when you put in some, get rid of some of those double bonds, the carbons actually sit together a little bit nicer and becomes a little bit more solid at room temperature. That's how we get things like margarine and shortening basically to be developed. That's why it's referred to as being partially hydrogenated, because they don't take out all the double bonds, but some of the double bonds in that case. All right, why don't you draw the product here of each of these and see what you come up with. Okay, and again, this first one obviously is drawn in a condensed type formula. So if it's easier for you to visualize, you could just turn that condensed formula into more of a structural formula, draw out your hydrogens and all that, so you can kind of see what's going on. Again, it might be a little bit easier to visualize sort of, what is happening here. So if we just did that, again, we're just drawing out the hydrogens here instead of a condensed formula. We'd obviously be adding our H2 to this case. And much like we've been talking about, I really am not concerned about any other part of this guy except right there where our double bond is located. And as we've been talking about, going to be identical, except turning our double bond into a single bond, which means right about here now becomes a single bond. Everything else identical. I'm just copying what's already there. And now I do have space, obviously, for my two hydrogens to come in. Again, they come in on opposite carbons in this case. So hydrogen there and a hydrogen there. Any questions on that particular one there? All right, same deal here. This is actually a cycloalkene. This is our double bond. This is a carbon. There's actually a hydrogen here, actually a hydrogen here. And again, we are adding H2, basically symmetrical addition. Works the same way as a non-ring structure. I'm still only concerned here where my carbon-carbon double bond is. That means I'm going to draw it identical to this, except I will break my double bond into a single bond. That technically means I still have the one hydrogen on each side. And now each of these carbons are short a bond. And that's good because now each can accept one more hydrogen there. And again, I'll make it a different color. These would be like the hydrogens coming in, if you will. Hydrogen there and hydrogen there. Really, since they're all hydrogens, you could also just draw this thing like that, and it would be correct as well, because it implies, obviously, that there are two hydrogens there. Any question on either of those two? So again, these are symmetrical additions. We've done a number of hydrogens, but very common hydrogen, two Cls, two Brs, all works the same as basically the hydrogen, except that you would obviously put Cl on both carbons or Br on both carbons. Any questions on those there? All right, then let's talk about some unsymmetrical additions. And unsymmetrical additions is when we're adding basically two different elements. So unlike adding two H's or two Brs or two Cls, we're adding some unsymmetrical guys in, or two different elements. And these are, again, sometimes referred to as being unsymmetrical additions. And most common one here is water. We can think of water as H and OH, adding an H to one carbon, OH to the other. Other common ones is like HCl, adding an H to one carbon, Cl to the other, HBr, adding an H to one carbon and a Br to another carbon. Now, in this case, because we are not adding two of the same elements to where that double bond was, there's actually a rule. And there's a rule which is referred to as the Markov, I spelled that really bad, Markov, the Markov rule, which basically says that the hydrogen atom will end up on the carbon that had the most hydrogens to start with. So whichever carbon atom, when you had the double bond there, had the most hydrogens directly attached to it is where you would add the hydrogen. And then the other element, either the Cl, the Br, or the OH, will end up on the carbon that had the least number of hydrogens. So this is sometimes catalyzed by a strong acid like sulfuric acid, sometimes abbreviated with just an H plus up on top, which means an acid catalyst. So for example, here, let's take a look at this particular one here and see, what is going to happen. Again, here, I'm going to redraw it out with all the bonds so we can kind of see all the hydrogens and everything. Might be a little bit easier to follow what's going on. So CH3, CH2, CH, double bond CH2. We're adding water, which is again what this is, which we could think of as H and OH. Again, you'll see the H plus here, which is a catalyst, or you may actually see H2SO4 written, which again has, really nothing to do with it. So here's the deal. You follow exactly what we did before, which is this is the only part that's going to change right here. So we can rewrite it exactly the same as before, where we go HCH, CH, CH, now making our double bond into a single bond, H and H. Now, one option would be to add the hydrogen to the left carbon, add the OH to the right carbon. So that's one option. Your other option would be exactly the same, but opposite adding. So I'll go R, H, C, H, H, C, H, H, C, again, making a single bond here. Now, our other option is we're going to put the H over here from the water and the OH over here from the water. These are really two options that you could get. Now, one is sort of correct based on Markovnikov's rule there about the hydrogen should end up at the carbon that had the most hydrogen to begin with. So what does that mean? That means when we look at our original carbon-carbon double bond, and we look at the carbon on the left-hand side, it has exactly one hydrogen attached to it. When we look at the carbon on the right-hand side, it has exactly 1 and 2 hydrogens attached. So based off of that rule, the hydrogen that's coming in should actually end up over here at this carbon because it had the most hydrogens to begin with, which means this would actually be the correct formula for this product, where the hydrogen ended up at the guy on the right-hand side where it had more hydrogens to begin with. OH ended up on the other side of the bond where we had the least number of hydrogens. This is what is considered the major product here. And that is always sort of what you should aim to draw. Is this sort of figure not really correct? The answer is sort of. This is what is sometimes referred to as the minor product, which means it doesn't happen all the time, most of the time. So again, for our class, you really should focus in on drawing the major product, which would be this guy. First off, any question on that addition there? Now, what did we end up with? Well, we started with an alkene, which, by the way, is 1, 2, 3, 4, 1 butene. And we ended up actually with this guy right here, which is an alcohol. So when you do a hydration reaction, you actually go from a alkene to an alcohol. And in case you're curious what the name of this alcohol would be, it is also named off of those alkanes. This has 1, 2, 3, 4 carbons, which is based off of butane. Because it's an alcohol, we drop the E and put OL. So this is butanol. And much like our double bond or triple bond, we need to give the location of where that OH group is at. And it's at carbon number 2. So this is 2-butanol. The 2 meaning the OH group is at carbon number 2. The butane part means there's 4 carbons. The OL means that it is an alcohol. Any questions on that there? Here. Let's try one more here. Got somewhere to scribble, maybe. And we'll scribble over here. So let's say we did, we had this here. This is obviously a double bond. We are adding 2 things that are not the same elements. So this would be an unsymmetrical addition. Same thing applies. This is really the only part we should change, even though it kind of maybe looks a little weird. So we're just gonna kind of copy it exactly the way it's at, and not really change anything other than messing it up here. Try this again. There we go. And coming down again, we're going to make that into a single bond. Coming down this way, this all stays the same. And coming the other way there, this all stays the same as well. All right, we've now made room in our double bond for the addition of the H and the Br. Now we have to look at our original double bond and see how many hydrogens this carbon has. This carbon has 1 hydrogen attached directly to it. This carbon here has no hydrogens directly attached to it. So the hydrogen will end up on the carbon that started with the most hydrogens. And in this particular case, that is the carbon on the right-hand side. And that means that on the right-hand side, we will put the H, which means the Br will end up on the other carbon here, and that would give us our major product. Any questions on that particular one? Or addition reactions? Again, symmetrical additions, all you have to do is break the double bond. 1 element to one side, same element to the other side on the carbons. Unsymmetrical, if 1 carbon had more hydrogens to begin with, then you put the hydrogen onto that carbon and the other element goes to the other carbon in the